In the last episode, we had a recap of gradient descent. We talked about the algorithm of stochastic gradient descent, how it relates to gradient descent, the loss function, and mini batches, and how it all relates. Today is the day we are gonna have a look at stochastic gradient descent. But this time we are coding it up. So I've prepared some code. If you've watched the last couple of episodes of this series, then you will recognize this class, for example, here the dataset class, the data loader class, the synthetic linear dataset class that we wrote, our model, well-known model, the linear regression, our objective function, the mean squared error, and the gradients of the mean squared error. And I've prepared two functions. SGD standing for stochastic gradient descent, and we got another function here, gradient descent. And the main function is also very simple, so forget the rest of the code here. This is just some plotting when we have a look at our plots. But what we want to do is the following. So in our main function, what we have is we generate some toy data, then we build out of that a dataset. We put that dataset into our data loader, and we will start implementing with gradient descent, and afterwards we will implement stochastic gradient descent and compare each other. And when we do stochastic gradient descent, we set the batch size equal to 1, because classical stochastic gradient descent works on each instance of a training data. And here you can see we are doing gradient descent, and here we're doing stochastic gradient descent, and then we compare the results and have a look at the plots. We'll train our model with gradient descent in 100k epochs and with a learning rate of 1 to the power of -4. We will also train our model with stochastic gradient descent in only 10k epochs with a learning rate of 1 to the power of -5. Thus, we will see that stochastic gradient descent will indeed need far less epochs than in the gradient descent case, as we have discussed in the previous theory episode. So let's start with gradient descent. So what do we have to do? Well, as always, we start with our model prediction and compute y hat with a whole batch of training data. Then we compute the loss with a mean squared error objective function. We shouldn't forget to compute the gradients. Then we can already update our weights. Well, for the model monitoring, we will also capture the loss here and the rates of the current epoch. Well, that's it. That is gradient descent. So let's do stochastic gradient descent now. So as always, we have our for loop over the number of epochs, as before also in gradient descent. And in the previous episodes we have implemented the data loader class that helped us to divide our dataset into mini batches of data, right? Currently the batch size is equal to 1, because in the classical stochastic gradient descent case we want to iterate over each instance separately. For monitoring purposes we record the losses during each iteration. So let's code it up. So what we want to do is we want the loss recordings, and then we use the data loader in order to get our batches. So currently our batch will only contain one instance. And now we basically do the same as in the gradient descent case. We are computing the model prediction, but this time on the training batch, so on a single instance, not on the whole batch. Then we do the mean squared error and record that as a loss. Then we compute the gradients. And then we can already update our weights. So as you can see, stochastic gradient descent is very similar to gradient descent. This part here is basically the same as in the gradient descent case. Just as I said, we are doing it not on the whole batch of the data, but on a single instance. And the single instance we get in this case from our data loader class. If you don't have an implemented data loader class, or you don't want to use a data loader class, for example from PyTorch, you can just loop over your training data. Optionally, you can also shuffle your training data before you iterate over it. And note, that's the most important difference between gradient descent and stochastic gradient descent, that in the stochastic gradient descent case, we are updating our weights on each instance, right? So here we are looping over each instance and we are updating our weights as we go over our training data set during one epoch, right? So this happens for the first epoch, for the second, for the third one, and so on. You get the logic. For monitoring purposes, we will trace the loss history for each iteration, and we will also compute the mean, but here it is, over all losses during one epoch. And of course also, we are also recording the weights. Well, that's it. That's stochastic gradient descent. So as you can see, implementing gradient descent and stochastic gradient descent isn't very hard, but you have to understand the differences between those two. The differences are subtle, but they exist. For more detailed information about the differences, you can revisit the last episode where we have talked about the theory behind stochastic gradient descent and how it compares to gradient descent. So let's run the script and have a look at the plots. So here we are with our plots. The first plot shows us the loss history across all epochs for gradient descent, and we can see that the loss is continuously decreasing until it converges. A loss value of approximately 24.7 is being reached after approximately 60k epochs already. When we have a look at the second picture, then we see that our model was being trained with gradient descent and it fits the data pretty good. Next, so we can see the loss history of stochastic gradient descent during the first epoch. I want to show you how these loss values are bouncing up and down. This is the noise that we have talked about in the last episode, which is inherent for stochastic gradient descent, since we are updating our weights after each training instance. So it's natural that our loss will bounce up and down, but the general trend will be decreasing. And we can see that when we have a look at our fourth picture, because here we have plotted the average loss history over the number of epochs. So what we did is we did a loss recording during each epoch, right? And we took the average of them. And each data point is such an average. And so we can see that the general trend is decreasing, and stochastic gradient descent reaches approximately a loss value of 24.7 in 10k epochs. So we needed 50k epochs less than in the gradient descent case. And when we have a look at our fifth picture, we can confirm that stochastic gradient descent worked and that our model is able to fit the data pretty well. And the last picture I want to show you is the loss history of stochastic gradient descent, which demonstrates pretty well how many iterations we needed in order to converge and how large the variance actually is. We can also see that the variance decreases with increasing iterations count, but the noise remains until the end as expected. You can see that the variance is decreasing because when you have a look at, for example, at each iteration, for example at the beginning, the variance is pretty huge. It goes from a loss value from up to approximately 1548 to going down to something like pretty near to zero, and it's oscillating up and down very much until it converges. Here you can see, for example, beginning from 1 million iterations, the variance doesn't change anymore. But as you also can see, the noise remains until the end. So here's something else I want to show you. Now I have changed the batch size. I've set it to 16 instead of 1. And so what can we see? So in the first picture we have again the average loss history over the number of epochs, and we can see that the curve is going down very smooth because it's also, as I said, the average for loss recording during each epoch. When we have a look at the second picture, we can also see that when we increase the batch size, we still have a very good fit on the data. And when we have a look at the loss history trace during the first epoch, we can see that we have less data points. That is because before we had 1000 instances, and when we had 1000 instances and we do stochastic gradient descent, we have 1000 data points during the first epoch, or during each epoch, but here we are having a look at the first epoch. And when the batch size is larger, then of course we have less data points, and we can see that here. And we can also see that we have still a lot of noise, but it's a little bit better than before. And we can also see that here. So this is the loss history with stochastic gradient descent over the number of iterations, and what we can see is that the variance is smaller than before, and this is also what we would expect, right? The smaller the batch sizes, the more noise we will have, and the more updates we will have during each epoch. But when we have a greater batch size, our training will get a little bit more stable, less noisier, still very performant. We still do a lot of updates during each epoch, but not as many as before. So when we are training with a larger batch size, we most often also need to train a little bit longer. But this doesn't have to be the case. I hope you liked this episode. We have learned a lot in the last episodes. We have learned how to fit a regression model. We have learned how gradient descent and stochastic gradient descent works. In the next episodes, I will show you more advanced techniques that are being employed in machine learning, like regularization, splitting the dataset into train, val, and a test set, and getting deeper into different kinds of objective functions. Stay healthy, and I see you then.